Imagine standing on solid ground. It feels steady, but beneath our feet, Earth is alive with motion. Deep below, immense power and pressure are constantly at work, sometimes breaking free in a sudden, violent tremor, an earthquake. The ground shakes, buildings sway, and the land ripples like waves on the ocean. Earthquakes are not random, they're the result of a slow, ancient process. Our planet's surface is a mosaic of giant plates, drifting slowly, shaping mountains, valleys, and oceans over millions of years. The story of an earthquake is the story of these plates. Pressure building for centuries, then released in a breathtaking instant. In places like Japan and California, people live with the reality that the ground can spring to life, transforming cities in moments. Yet, these forces also create the Himalayas and Andes were pushed skyward by the same energy that shakes the ground. Earthquakes are a fundamental part of our planet's life, a process of destruction and creation on a scale almost beyond comprehension. To understand why the Earth shakes, we must look beneath the surface and explore the hidden machinery at work. By studying the science below our feet, we learn how these movements happen and how to live alongside them. The story of an earthquake is not just one of danger, but of discovery, a reminder that our planet is wonderfully dynamic. To understand earthquakes, we must journey deep inside our planet. At the center lies the inner core, a solid, superheated ball of iron and nickel squeezed by immense pressure. Surrounding it is the outer core, a swirling ocean of liquid metal that generates Earth's magnetic field, shielding us from solar radiation. Above that is the mantle, the planet's largest layer. Mostly solid, it moves slowly like thick honey driven by heat from below. This slow churning, convection pushes hot rock upward and cooler rock downward, powering the movement of continents. Finally, we reach the crust, Earth's thin, brittle outer shell. There are two types: dense, thin oceanic crust beneath the seas, and thicker, lighter continental crust beneath our feet. All life exists on this fragile shell, which is broken into giant pieces, drifting atop the mantle. These drifting plates set the stage for earthquakes. The crust may seem solid, but it's just the surface of a restless, layered world. Understanding these layers reveals the forces that shape our planet. The drama of earthquakes begins deep within, but its effects are felt on the surface. Our journey to the center explains why the ground sometimes shakes. Earth's crust is fractured into massive tectonic plates, like a global jigsaw puzzle. These plates, carrying continents and oceans, are always on the move, driven by the churning mantle below. They drift at the pace of growing fingernails, but over millions of years, this movement reshapes the planet. The real action happens at plate boundaries, where plates meet and interact. Boundaries are jagged, active zones pulling apart, colliding or sliding past each other. Each type of movement creates unique landforms and triggers geological events. These boundaries or fault lines are where most earthquakes and volcanoes occur. The friction and stress from plates grinding together cause the ground to tremble. Maps of earthquakes and volcanoes trace these boundaries, revealing the restless nature of our planet. The story of Earth's surface is written along these fault lines, in trembling ground and fiery mountains. Understanding plate tectonics is key to understanding earthquakes. What happens when an earthquake strikes? It starts with the slow movement of tectonic plates. At boundaries, plates get stuck due to friction, even as the rest of the plate keeps moving. Stress builds up along the fault, bending and straining the rock like a stretched rubber band. When the strain becomes too great, the rock snaps, releasing stored energy in a sudden jolt, an earthquake. The underground point where the rock breaks is the focus. The epicenter is the spot directly above it on the surface. The break sends out seismic waves, vibrations that travel through the earth. First come P waves, compressing and expanding the rock, then S waves, shaking the ground side to side. Finally, surface waves roll along the ground, often causing the most damage. The combination of these waves makes the ground roar and buildings crumble. Earthquakes are the planet's way of releasing built-up energy. Each quake is a reminder of the immense forces at work beneath our feet. The science of seismic waves helps us understand and measure these powerful events. The birth of an earthquake is sudden, but its story is centuries in the making. The way plates move creates different types of faults, shaping the earthquakes we experience. Normal faults form where plates pull apart, causing one block to slip downward, common at mid-ocean ridges and rift valleys. Reverse or thrust faults occur where plates collide, pushing one block up over another, building mountains like the Himalayas and causing powerful quakes. Strike-slip faults happen where plates slide past each other horizontally, as seen in California's San Andreas Fault. Each fault type tells a story about the forces shaping the land. By studying faults, geologists learn how plates move and what hazards exist. The landscape itself, trenches, mountains, valleys, reveals the drama unfolding in the crust. Faults are the front lines of geology where slow plate movement becomes sudden, ground-shaking reality. Understanding fault types helps us predict where earthquakes are most likely to strike. The world's great faults are the stage for Earth's most dramatic events. Earthquakes aren't random. They cluster along tectonic boundaries. The Pacific Ring of Fire is the most active zone, circling the Pacific Ocean and marking the collision of major plates. Here, subduction creates deep trenches and powerful thrust faults, generating massive earthquakes and most of the world's volcanoes. The Alpide Belt, stretching from the Mediterranean to the Himalayas, is another hot spot, formed by continental collisions. These zones shape mountain ranges and bring frequent, powerful quakes to countries like Turkey, Iran, and Nepal. Sometimes earthquakes strike far from boundaries, so-called intraplate quakes, when stress builds along ancient faults. These rare events can be devastating in unprepared regions, as seen in the New Madrid earthquakes. Mapping these hotspots helps us identify communities most at risk. Understanding where the Earth trembles most is vital for safety and preparedness. The restless movement of plates defines the world's seismic hotspots. How do scientists measure earthquakes? With seismographs, sensitive instruments that record ground motion. A seismograph's weight stays still as the ground moves, tracing a seismogram, a record of the quake's vibrations. Modern devices detect even the faintest tremors, turning chaos into data. Scientists measure magnitude, the total energy released, using scales like the moment magnitude scale. Each step up means 10 times more shaking and 32 times more energy. Intensity measures the quake's effects at specific locations, using the modified Mercalli intensity scale. One earthquake has one magnitude, but many intensities, highest near the epicenter. Local geology can amplify shaking, making some areas more vulnerable. By analyzing seismic data, scientists pinpoint a quake's location and depth, crucial for emergency response. Seismology turns the Earth's rumblings into knowledge we can use to stay safe. Can we predict earthquakes? Not yet. The processes happen deep underground, hidden from view. While we can't predict the exact time or place, scientists can forecast the likelihood of quakes in certain areas over decades. These forecasts help communities prepare by strengthening buildings, planning responses, and educating the public. Technology now provides early warnings. Sensors detect the first fast P waves and send alerts before the destructive waves arrive. Even seconds of warning can save lives, allowing people to take cover and systems to shut down. Since prediction isn't possible, preparation is key. Engineers design flexible buildings, governments enforce building codes. Individuals need emergency kits, plans, and knowledge of what to do when shaking starts. Preparation is our best defense against earthquakes. Science, engineering, and community action together reduce risk. While we can't stop earthquakes, we can be ready for them. Earthquakes remind us that our planet is alive and ever-changing. The slow drift of plates builds mountains and carves oceans. Sudden quakes are part of this grand process. Science has transformed our understanding, turning fear into knowledge and preparation. We now identify risk zones, measure forces, and develop strategies to live safely on a restless Earth. Collaboration between scientists, engineers, and communities is essential. From earthquake-resistant buildings to early warning systems, human ingenuity helps us adapt. Our safety depends on learning to live with the Earth's movements, not stopping them. Earthquakes teach humility and the value of community, neighbors helping neighbors, rebuilding together. By exploring the science beneath our feet and preparing for the future, we can thrive on our dynamic planet. The story of earthquakes is one of challenge, discovery, and resilience.